Welcome, ladies and gentlemen, to my step 6 presentation. I'm Alireza Alizadeh, and this is CS Internship. In this step, our primary focus was on classifiers and learning. So, the reading material and the study items mostly concern classification. And before diving too deep into classification and what classification is, we need to talk about learning. So, how do we learn? For machines and for computers, we have a couple different types of learning. The first one is supervised. So we have three different types, right? One is supervised. One is unsupervised. And the other one is reinforced. So reinforced. What's the idea behind these? So think about it this way. You have a bunch of data, right? Bunch of data. If your data has labels, so for example, I have a database of a bunch of cars. So I have car 1 here and 2 and 3 here. And I have classified these and I have given them labels as sports cars or family cars and so on and so forth. When my algorithm comes and looks at this data and learns based on these labels that we have, that's supervised. I'm supervising my algorithm. I'm looking at it and I'm telling it that, look, this is what the true label is. So take that in mind and be careful and take it into consideration in your calculations. When you do this, it's called supervised learning. We have another type of learning which is unsupervised. This is particularly good for finding patterns in data. So take this for example. You have a bunch of data and they are scattered all over the place, right? And you don't have any labels for them. You don't know what their class is. You have no idea how they behave. But you want to learn something from it. You want to extract something out of this. So what you do, you use unsupervised learning. And one thing that you can do with this is clustering, for example. So you have something called clustering. What clustering does is basically comes and looks at this data and says, okay, I don't know what this means, but these are bunched up together. We'll maybe include that one as well. And these are also bunched up together. So here's a pattern for you. Now you have more ideas about your data set and you have more information about it. The other thing is called reinforcement learning. What is reinforcement learning? Well, let me tell you. It's not really that complicated. So think about this. You have an agent, an algorithm, and it performs some action. So you have an agent. It does some action. And based on this action, the state of the agent changes. So you go back with a different state. Also, you give it reward based on this action. So reward. Please note that reward can also be punishment. So for example, if it did a good thing and it, edged closer to its goal, then it's, a reward. And If it did a bad thing, then you give it punishment, and it learns based on those rewards and punishments and adjusts its, calculations and algorithms. So these are the basic three types of learnings and how you go on about, your algorithms and what's your approach based on your data. After this, in our study items, we get to a point that we are presented with a basic idea of how machine learning algorithms work, which is basically we clean the data and we choose an algorithm and we then make it better and improve it. But the most prevalent subject in this step is classification. So we're going to work with classification. In classification, you have a bunch of labeled data. So you have a bunch of classes. So, for example, 3 classes, and your data is labeled based on these classes, for example, 1, 2, and 3. And your goal is give this model new data, and predict these classes. So predict. So it's very simple in principle. You have a bunch of data, you have a bunch of input that usually would be a part of one of these classes, and you want to predict that without knowing it beforehand. And it falls under supervised learning. So all of this is supervised, since I'm giving it the labels beforehand to train it, and then moving on to predicting. So all of this is supervised. For this, we're going to look at an example that we have here. The example is a bunch of medical data. So our data is medical, and we want to predict the risk of, heart problems and heart diseases in our patients. The data that I'm using is from Framingham Hospital, and you can find it in Kaggle, I believe. And the model that we're going to use is a logistic regression model. And we're going to do a bunch of pre-processing before going into training, and some other subjects might dive into our conversation, which are a bit out of scope in this step particularly, but it's good to know, and it's inevitable that you are presented with these ideas and you have to challenge yourself to work around them and understand them. So what are we going to use? We're going to use pandas for our data here, and so this is for handling data. NumPy is for our calculation. These two are for visualization, and these are for our model training and evaluation. So let's get on with it and load our data and see what's up. Okay. So data is in CSV form. Lovely. We love a CSV data set. So you can see here we have a bunch of columns. We have sex, which is here presented by male, which 1 is male and 0 is female. We have age, education, current smokers, cigarettes per day, and if they are on some medication, if they've had a stroke, if they have diabetes, what's their cholesterol, what's their blood pressure, and so on and so forth. And this column right here is what we want to predict, the risk of them having heart problems in the next 10 years. So let's dive a bit deeper into our data and see what's up. We see in our data set that we have 4,238 entries. However, when you look at the non-null counts here, you see different non-null counts. For example, this one is different. This one is way different. It's in, in the high 3,000s. So this shows us that we have a bunch of null data, basically empty fields in our data. And when we look at it, using df-describe to, get some idea of count and stuff like that, you see that counts are different, which basically means null data again. And something else that you might see here is that in our quartiles, we have a lot of zeros, which is a bit weird, which means some data is not really on the same scale as the other data. However, dealing with null values and pre-processing, we need to speed up here a bit. We see here that we have a bunch of null values in education, 6 per day, med, so on and so forth, and we need to deal with this. One way is to just drop these columns. The other way is to fill these null values. I'm going to drop education because I don't think it really matters when you're dealing with heart disease. Okay, if you can make the argument that somebody who's educated can take care of themselves better, therefore they have a lower risk. However, if they would take care of themselves better, it would show in their medical data, such as cholesterol, BMI, blood pressure, glucose, and stuff like that. So what are we going to do is drop that. We're going to drop education here and work with the rest of our data. So how are we going to go on about filling in these empty fields in our data? What I did was basically, for males and females act differently. So I got an average of the column that needed to be filled, and that average was grouped by male or female, and I filled the data in accordingly. And we do this a bunch of times. We repeat this for every single column that needs their data to be filled using, group by, mean, and fill NA. And then we have, a uniform data set and a data set that doesn't have any null values, so we can go and train our model. So this is the same process, just repeated over and over and over again. So I'm going to just skip these since they're basically acting the same way. And this is the output. As you can see, we don't have any null values anywhere. So here you can see our distributions. This is just a discovery method. This is just to see how your data is, how it's working and stuff like that. I also excluded the binary data from this because I don't think it's really relevant to, get a histogram of binary data. Anyway, and here we have an outlier analysis, and we see we have outliers. However, in medical data, for example, a high blood pressure or high cholesterol doesn't really mean bad data. It's insightful. It gives you more information, and it's actually relevant to the risk of heart diseases, or low cholesterol, or low blood pressure. So we're keeping these seemingly outliers in. And moving on from that, we're gonna drop our column that we want to predict from our data set, which is the 10-year CHD. And after that, we're gonna have a bit of more exploration and get a heat map and see how the data correlates, which correlates somewhat nicely in some places, like here with, blood pressure and, oh, I have to move down, with like blood pressure and BMI and stuff like that. So this is still like in the exploration phase. Now we need to work with our model and train it. So we're going to use logistic regression here, and for our solvers we are using liblinear. Why? Liblinear is particularly good when you have a binary classes, so 2 classes in total. And it's also good when you have a small data set, which we do. We only have like 4K rows, so 4,000 data points. So we're going to use that. And we're going to use cross-validation to get the best model. In this case, we're using tenfold, so 10 splits of data. You can see it here. And we're going to train our model now. So how do you train your model? You split it into 10 different parts, and you use this ILOC from pandas to get your train and test sets for X and Y. X here is all the data, Y here is 10 years CHD. So these Ys are 10 years CHD. So 10 years CHD. Anyway, we have trained our model here and we are choosing two different models. One based on recall, the best recall that we have, and one based on accuracy. And why are we doing this? This is based on an experience that I had in university, which we had a bunch of models. One of them had very low recall and the other one had lower accuracy but better recall. And sometimes, depending on your purpose, it's better to prioritize one of these metrics, so accuracy or recall and so on and so forth. So let's look at the models that our logistic regression has come up with. So the first one is the best accuracy one. We see here that we have 88% accuracy. That's pretty good. However, if you look at the one prediction, which is that the person actually is in risk of heart problems and heart diseases, it's really low. And this is a problem. And even the best one that we have has also low recall for one. Why is this a problem? We're going to get to it. Just bear with me for a second here. So something seems to be wrong here, because this basically means our model has learned nothing and is basically predicting zero all the time and getting away with it. Why does this work? It's probably because our data is not balanced. So we have a lot of zero classes. So for example, like we have 3K of these, but for example, we only have like more than 3K plus, and we only have like 500 of these. So how do we tackle this and improve our recall? We need to use class weights. So if we make our classes weighted and make them balanced, which means, okay, it's true that we have less classes, but they have more meaning to them in the one class. So if we use this special parameter and make our classes weighted, and we also use a scalar just for good measure and scalar data, so they are more in the same range of each other, and like you don't have data from 1,000,000 to 0 and like one is like between 0 and 100, we get some different results with our models. So for example, look at here, our accuracy has been reduced. Instead of 88, now we have 70 here. So we don't have 88 again, which is okay, 70% is good, but we have a lot better recall in both our classes. And if you want to especially like go all in maximizing the recall on the one class, you can do it with the best recall model that we also trained. And you can see it here. It has a better recall overall in the one class. Why does recall matter? Why am I so obsessed with getting a better recall, even though our accuracy has suffered and is now 70% instead of 88? Let's look at this picture here. This is what our metrics mean. This is accuracy here. This is recall. While accuracy is good, it's true positive and true negative. You can imagine if you have a lot of true negatives and true positives are just 0, you can still get away with it because this is going to compensate for you. However, in recall, it's all the positive cases. So for example, all the people in risk of heart disease that you were able to predict from the whole data set. So true positive and false negative. So the ones you predicted wrongly that were positive, and the ones that were actually positive are here in this, relationship with each other. And it shows you a more important metric because you are actually measuring how good you can predict someone who is in risk. But in our other models, you were just basically predicting someone who's not in risk. So in medical problems, I think it's more important to, focus on recall, because predicting someone in risk is more important than, someone who's not, because someone who's not in risk doesn't need help, but someone who needs risk needs help, and recall helps us to calculate that risk, predict that risk better. So that's why I decided to obsess over recall and the low recall, and make the model actually a bit useful, even though we lost some accuracy. So we lost a bit of this in the process. But as I said, the first model wasn't really learning anything, and it was just saying, yeah, not in risk, and getting away with it. And accuracy can be a bit misleading. Anyway, that's the end of our presentation. If you have any questions, type it in chat. If not, this is the end. And we're going to say goodbye. Thank you for watching.